In this amazing video, we will discuss different types of data types available in SQL to use in SQL Server. We've already seen some data types because you've been manipulating tables for many weeks now, but we'll talk about different aspects of different types of data types, do some experiments, and illustrate some techniques, not always through querying tables, but just by writing simple statements in a query editor window. To follow along, you should log in with the grocery store credentials available on Blackboard and not repeated here for security reasons. Here are four broad categories of data types. Data stored as strings, or also called text. Data stored in numeric formats, including floating point and integer formats. Data stored in date and time formats, or sometimes those formats merge together. And data stored as binary information. We will talk a little bit about each of these data types throughout this presentation. Designing a database is when deciding what data types to use comes into play. It is extremely important, it is crucial to put enough design into your project to try to overcome any problems you may have down the road. A bad design will result in a bad product. Questions to ask yourself, and since this is not a design course, we will not spend too much time on design, but it's good to have some context. What will you do with the data? Will you perform calculations on the data? Will you store it for presenting on a web page, or presenting on a report, or presenting to a mobile device? How does the data get to you? Does it come from an external source like another database? Or perhaps are users typing in the data from data entry forms on web pages, on desktop apps, on mobile device apps? What do you have to do to make sure that data is correct? Do you have to check it for range limitations? Do you have to check whether or not zip codes are typed in correctly? Do you have to check whether or not names are spelled correctly? Finally, if the database is significantly large, there is always the issue of scale, and the concern is, how is that data being stored? Is it efficiently being stored? If the database is tiny or relatively small, do we really care if it's stored efficiently? Another aspect that we are not going to discuss in this class, but I will add here, is normalization, which is the way that we store data efficiently, or one way, in a database. In the second semester of this course, the second course in the sequence, we will discuss normalization in great detail. But it is a significant issue during the design of a database. Fundamentally, and hopefully obviously to you at this point, we do not store everything as a string. We do not store everything as text. We could literally store everything in long, tremendously long strings of text. Nchar, varchar. But that would be a horrific nightmare, putting the data into those strings and retrieving the data out of those strings. So hopefully we take the time to learn the different data types available to us, their features, their limitations, their capabilities, and then pick data types that are appropriate. In this case, I picked a table from the grocery store database, and we have an integer as our primary key, a numeric value. We have a time data type, storing the time of the transaction. We have a date data type, storing the date of the transaction. We have four foreign keys, store, loyalty, transaction type, and employee, which are all integers. And we have a comment. The comment is defined to be the maximum possible value that can be stored in a character string, which is a very long comment. just because we can store everything in a string doesn't mean we should. And here are some general reasons, aside from the obvious reason that it would be a big mess, of why we don't store things as strings. You can't do math on a string. In order to do math, you would have to convert that string to a numeric data type and perform the math, and then perhaps convert it back if you made an edit to those values. We can't sort the way we might like to sort. We can sort strings, certainly in lexical order, dictionary order, but we can't sort by dates, we can't sort by numeric values, and we can't do the validation we might need to do. You can't validate a date if it's not stored as a date without writing a lot of extra code. So it's important to understand the data types that are available, to work with them, get experience with them before you start designing a database. Here are some dates. Once again, I use the grocery store database. And the default format to display that date value is year, month, day, which is a common format in many parts of the world, not necessarily in the United States, but we get used to it. And if you take a look at the structure of the table, I'm going to flip over to SSMS. I've already typed in the query that we just saw on the slide. If you look at the structure of the table, the date of transaction is a date data type, meaning I can store a date in there but not a time. I arbitrarily elected to store the time in a separate field from the date. I don't have to do that. I could use the SQL Server date time data type, but to me it makes more sense to store the date separately from the time. I'm not saying it's better, I'm not saying it's worse, it's just a habit that I have. So when you are designing, when you are looking at other people's databases, you may see date and time stored together in a date time data type, but in this case I have a time data type and a date data type to separately store the time and date of the transaction. Back to the slides again. We can do some nifty things with SQL functions that are provided to us by Microsoft, the manufacturer of SQL Server. And we can get a list of some of the things that are available simply by starting to type. So you can see here that if I type date, it automatically tries to think about what I might want to use there, and it shows me the things that start with date. I can use date add to add two dates together. I can use date diff to compute the difference or the distance between two dates, and the other neat things I can do there. So I encourage you to experiment with those functions, see what they do, try to come up with interesting expressions based on those functions, and also research them online and in your book. It's a very bad situation to be in when you find out that you have written a function or a stored procedure to do something that was already available to you in the SQL language that you're using. As for example, we would not want to write a date add function and then find out after spending a week doing that that there was already a date add function in SQL. Let's flip back over to the SSMS window and let's see what might be available to us just as a way of experimenting. What is date name? It says it's a built-in function, as most of these are. It requires an interval, a date, and it returns a varchar of length 1. That doesn't tell me a lot if I don't already know what the function does. So let's be detectives and let's go over to our browser let's build a search phrase that will tell us a little bit more about what we'd like to know. Again, we were interested in date name. And as you can see, Google is already familiar with this search. Many people have already done this. But this is a good way to learn about the tools available to us. You're certainly comfortable reading a book. If you'd like to do that instead, feel free. But we can probably find some interesting resources just using Google or any other search engine. So a reasonable search phrase appears to be SQL, structured query language, date name function. You may want to narrow it down even more. There may be a case that date name, the date name function, exists in other database engines like Oracle or MySQL, and you may get some results that you have to filter. But if you specify SQL Server as a product, that's the Microsoft product we study in this class, then you can eliminate those other database engines or eliminate some extraneous results that you might not want to look at. We have a very brief explanation here. So Google has summarized what they think is a popular result to this search phrase. And it says the function returns a character string that represents the specified date part of the specified date. For example, you can pass in 2021-01-07 and have SQL Server return only the month January, which is mildly interesting and might help you down the road when you're doing date manipulation. And this link comes from a site called database.guide. I'm not familiar with that site at all, but since Google recommended it and we're being detectives, let's just see what we get. I am going to look for an example because we learn by examples. And here's something that I can copy. Flip back over to SSMS. Remember that I can highlight, and only that highlighted code will run. And I get January. This is interesting to us for another reason. We're demonstrating that we can test and exercise and play and experiment with these functions without having a table. All we need is a select statement, and in this case we used a string literal as a date without even referencing a column in a table. Again, a quick and easy way to do some experimentation with data types, conversions, and functions. The result here that was I got the word January, and that's kind of what the function tells me. The word name there tells me that this function will return named things, semantically interesting things like the word January, or perhaps the day of the week. How do I get the day of the week? I'm guessing maybe day will work. Let's try that. Well, it didn't. I got a 7. So instead of the day of the week semantically, I got the day of the week numerically. But as you saw a moment ago, if I use the word month there, I got the word January. So we would do a little more research, a little more experimentation, a little more reading to try to figure out how to get the name of the day of the week rather than the numeric value of the day of the week. But hopefully you're a little bit inspired and you're willing to do some extra work to learn just how date name works and just how it might be useful to you down the road. We will continue with our slides. Here's another function that I already searched for called datePart. In the datePart function, there are some interesting results that Google provides. The first result from this search phrase was from a website called W3 Schools, which is a relatively popular website for a lot of different programming languages, software development, and SQL. So we often reference W3 Schools when we're searching for something useful. The second result in this search is the date part function provided by Microsoft, which is the authoritative resource on this function because SQL Server and Transact SQL belong to Microsoft. These are both good resources for you to use to learn more about date part. You could also look in your book. You could also look in other books, but if you need a quick example or you need an overview of how the function works and all the different arguments that can be passed in, these are both good places to start. Here's an example of date part. I'm extracting the month number from the date of transaction in the transaction table in the grocery store database. I can copy this code that I provided at the bottom, go back to SSMS, and I can run that. That gives me month number 1, which I assume is January, because the date of transaction in the first row is 2012-0101. The 2012 is the year, the first 01 is the month, the second 01 is the day, and the month number is 1, meaning January. Back to the slides. On the next slide, here's what happens if we don't do it right. We try to get the month, date part M, from the time of transaction column, which is wrong because there is no month in a time. And I get the error message, the date part month is not supported by date function date part for the data type time. So hopefully that's enough of an error message to trigger my thought process and I realize that I used the wrong data type with the date part function, or I used the wrong function on the time data type, depending on what I was after. But if we do get an error message, it's not time to panic. Read the error message carefully. Try to figure out what it's telling you. Go online and search for the error message in its entirety, or search for portions of the error message, or become adept at building a search phrase that will help you figure out what the problem is. Because part of the skills that we have to develop as database managers and even as programmers is to build good search phrases to solve these problems. You're certainly welcome to crack open your book and try to figure out what went wrong using the book, but in most situations you will be much more efficient using a search engine to try to solve a problem like this. Moving on, let's talk about integer data types. These are a subset of the numeric data types that we saw earlier. A common mistake that developers make in programming languages, in SQL, in all kinds of computer applications is the concept of integer math versus floating point math. So in the first example here, I have provided a SQL statement. Again, notice it does not use a table. It just does a mathematical calculation on two constant values, 50 and 100. And it divides 50 by 100 and it gets 0, which to an experienced developer looks perfectly fine, but to a civilian or someone who's first learning this topic looks a little bit weird. 50 divided by 100 is 0.5 to most people. But since we're using integers, 50 is an integer, 100 is an integer, 50 divided by 100 is 0. There are no decimal places. Integer divided by integer results in integer, and we get 0. It's not broken. There's nothing wrong with this. It's doing exactly what we told it to do, but we didn't expect that it would be that precise in what we told it to do. At the bottom, here is and I'm not going to say this is a corrected version of this because it's not. It's just a different version. In this case, the 100 has a decimal point after it, meaning that it is a floating point number. Now remember, as you read in the book, You cannot do math, you cannot do an operation like this on two different data types. Well, this expression has two different data types. 50 is an integer, 100 is a floating point number. SQL will implicitly convert the 50 to a floating point number and do the math in floating point math. And you can see in my little screen snip, you get 0.5, which is the answer that most people expect when they divide 50 by 100. Make sure you know the difference between integer math and floating point math, because it will carry you through Java and through C# and any other programming languages that you apply. And it will also save you a lot of time and trouble when you don't get the answer you expect. Let's copy this and go back to SSMS again and run it. We do get 0.5. What if we put a dot there? Now we have floating point number divided by floating point number, and we will get the same result, 0.5, because we are maintaining decimal places because we're dividing float by float. Just to go through this again so it's a little more clear, when we have a 50, which is an integer, divide by 100, which is a floating point number, 100 point. And if this isn't clear enough, feel free to put in a 0 after it, because sometimes it's a little more obvious that that's a floating point number when you have a trailing decimal place. Integer divided by float cannot be done. It's impossible. So SQL Server converts the 50 to a float. That leaves us with float divided by float, and that works. That can be done, and that answer is, of course, 0.5. Here's another quirk of integers. We have a situation called overflow. We'd like to know how big an integer can get. And in this demonstration I'm showing you, I'm starting with 2,147,483,647, which is 2,147,483,647. That is the biggest value we can store in an int. That's great. But if we try to increment that by 1, we create integer overflow and the program breaks. Let's grab all of this. Back to SSMS again. Let's run this. Notice that there are two select statements. The first select statement generates this result in the results pane, because that's the original value we put into that variable. The second select statement causes an overflow, which generates that red message in the Messages tab. And the error says arithmetic overflow converting expression to data type int. That's a little bit daunting, but once you work with it a little bit and you realize what overflow means, then you can go looking for the expression that hurt you. There's no way around this using ints. This is the biggest number we can store in an int. An integer can go from negative 2,147,483,648 to positive 2,147,483,647. The reason the range is not symmetric, it's a little bit bigger on the negative side, is because we have to account for a 0 in there. Flipping back to my browser again, I have prepared for you in a Google search the range of these integer types. Should you memorize these? If you're a nerd, yes. Otherwise, just know where to find them and know that there are limitations. That's the biggest takeaway, is that there are limitations in these data types. They cannot exceed certain limits. And a big int is 8 bytes wide, and it can go from -2 to the 63rd all the way up to +2 to the 63rd minus 1. These are powers of 2 because we store numbers in computers as powers of 2. And then the smallest integer type is called tiny int, which goes from 0 to 255. And I will tell you that You were probably better off doing everything with int in general, even if it is a very, very small quantity like 0 to 255, because you may appear to be saving some efficiency, but you're probably not, due to the way computers store information. And typically the smallest unit of measure is going to be an int, or the most efficient unit of measure. And you'd have to do some experimentation and read up on how your database stores these values. But when in doubt, if you're creating a table, use int, unless you don't have enough space in an int. But if you have a tiny value, even resist the urge to use a tiny int, resist the urge to use a small int, and just use an int. Now that is a very, very general guideline I'm providing. Okay, that's not something to go to war over. That's not something to fight over. I'm just telling you that in general, an int is the most efficient way to store information. Back to the slides. Floating point numbers have slightly different types of ranges. They have a number of decimal places as well as an exponent limit. I won't get into that in too much detail, but I just illustrate a interesting quirk I can play with these floating point numbers to illustrate a problem you can get into. On this slide, everything looks great. 3 by 10 to the 45th plus 4 by 10 to the 45th. The E stands for exponent. So we have a 3, and then the 45 is the power of 10. 3 times 10 to the 45th plus 4 times 10 to the 45th. And the answer, as you would expect, is 7 times 10 to the 45th. And that works. You're welcome to copy and paste this SQL statement if you like. But on the next slide, I'm throwing you a curve. Look closely at this. I'm adding 3 by 10 to the 45th plus 4 by 10 to the 45th, which we already saw is 7 by 10 to the 45th. Then I'm adding 1, which is way, 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 way out there at the end of that number. After I compute that sum of those three numbers, I subtract from that what should be 7 by 10 to the 45th, but look what I get. I get 0. I will grab this and take this over to SSMS. And you will see that I do get 0. What I'm showing you here is that while I have a very large number, I don't have a large number of digits I can store, meaning that the vast majority of those digits are going to be zeros way, way out into the less significant figures. So, yes, you can store big numbers, but you cannot store them to a high precision. And I'm not going to go into any more detail than that, but I want you to understand, I want your takeaway to be that even though I can store big numbers, I cannot store precise big numbers. Here's another function built into SQL. I grabbed this from the authoritative source, Microsoft.com, and I note that it applies to SQL Server starting with 2008. There are some of those installations around, believe it or not. It's only been over 10 years. Azure, which are SQL Server cloud databases. Azure Data Warehouse, which is a cloud database configured to store high volumes of data for efficient retrieval. Data warehouses are not a topic in this class. And then parallel data, which is something else altogether. But this function is available to us because we are using SQL Server. So we have a nice authoritative resource here. What does this function do? Well, it converts an int ASCII code to a character value. Well, what does that mean? On the next slide, here's an example. We are using the function and we're passing it the value 100, and it is giving us a D, a lowercase d. The lowercase is important here. We haven't been very case sensitive throughout our study of SQL Server, but all of a sudden now that lowercase d does matter. Grab that code. There's our lowercase d. Now let's just make one small change to this. How about 101? 101 is a lowercase e. How about 102? Can you guess what 102 is? Whoops, sorry, didn't highlight it. An F. We saw D, E, F passing at 100, 101, and 102. A pattern is building. How about 103? Oops, hit the wrong button. G. We saw D, E, F, G using 100, 101, 102, and 103. We're seeing a pattern then that these numbers seem to correspond to values in the alphabet. Well, that's correct. And the values in the alphabet are defined by something called the ASCII chart. And if you haven't seen the ASCII chart, if you're not familiar with it, this is a great time. Stop, take some time, and study it, because it will be with you for the remainder of your career, because it defines the numeric values that correspond to letters. And since everything in the computer is stored numerically, we need a way to map letters and punctuation and all the things on the keyboard into numeric values so we can store them efficiently. And that mapping from numbers to letters is the ASCII chart. All of these will be the same. Some of them are just easier to read. This one has 4 columns, 5 actually. Decimal values, or base 10, hexadecimal base 16, octal base 8, HTML codes, and then what the corresponding character is. Look at 100 in the 4th column there, in the 4th major column. There's our D. 100 is a D. What we're learning then is that the purpose of the CHAR function is to map a numeric integer value into a letter from the ASCII chart. That's what CHAR does. Here's an example of misusing CHAR. The ASCII chart only goes from 0 to 255. It actually only goes to 127, but a lot of people consider it 0 to 255 as ASCII. If you go over that number, you'll go over 255, and you pass that value to the CHAR function, you get a null, because there is no mapping beyond 255. Interestingly enough, no error, but we do get a null value returned by the function. So it's well behaved, but it doesn't give us quite what we expect. Binary types. We'll do a little bit of this. We'll touch on this just to give you some exposure. Binary data is bits. You can't read it. Some examples are executable files, MDFs, videos, audio downloads. We can't open it up with an editor like Word and go through it and read it and edit it. It's not that kind of data. The opposite of binary data would be probably text data or character data. Binary data, although our computers lay things out in bytes, binary data is not typically or guaranteed to be stored as bytes. It's a string of bits that happen to be broken up into groups of 8, but they are not considered characters, as an individual byte is usually considered a character. So yes, we may have 1,000,000 bytes in a binary data file, but that is not necessarily 1,000,000 sets of 8 bits. It's 1,000,000 times 8 bits all strung out together. And SQL Server supports a binary data type, a variable binary data type where you provide an argument, and then a variable binary data type where you simply specify the keyword max, meaning that that's as much as it can possibly store. The third example is about 2 gig as far as I know, and if you find yourself needing to store 2 gigabytes of binary data in a data item in a table, then good luck to you. If you find yourself needing to store more than 2 gig, then you probably need a different kind of database manager because you're exceeding the value of that data type. Here's an example, because you were probably asking yourself, how do you get binary data into a table if you can't type it in, since you can't read it? And the answer is to use a function called openRowSet. And in this case, I provided you with some SQL code that illustrates how to read from a file, helloworld.exe in this case, into a binary variable in a SQL statement. You will not be doing this. I will not ask you to do this in a homework assignment. As a matter of fact, you can't do it because the file path that is referenced in the SQL statement is relative to my server, not to your local client. So even if you had a binary file that you wanted to read into one of your tables, you wouldn't be able to do it unless you could get it onto my server. And I'm not going to let you do that. So here's an example. We won't ask you to write homework that does this. We won't do any more than just discuss what was on this slide as far as binary data goes. This has been then a brief introduction to data types and a few functions. I encourage you to be curious and inquisitive, and I encourage you to look at some of the functions that are available. Fire up SQL Server, play around, see what you can get these functions to do. Work with dates, work with floating point types, work with integer types. If you'd like to know more, highly recommended, go to YouTube, find SQL Server videos that discuss data types, and dig in, because these are things that you will be using throughout your career to manage data.